Hello everyone, in this video we present our work on multimodal interpretable depression analysis using four modalities which are visual, physiological, audio and textual. Depression is a global concern and its early detection is helpful for better treatment. The traditional methods used for depression analysis, for example interviews and self-reports, are subjective and prone to bias. We need automated, objective, data-driven methods. Particularly, multimodal methods are very helpful because they utilize the most informative cues from each modality and provide more comprehensive insight compared to unimodal analysis. Interpretability is also helpful to understand the contribution of each modality towards the final depression class that is detected. Researchers have utilized visual information such as facial expression, body language, and attention-based information. They have also explored physiological information, although limited studies have been found because getting the physiological information, for example plethysmography signal, require us to use certain sensors, which is not very convenient. When we use sensor to capture PPG signal, it's called contact PPG, whereas when we use RGB camera to remotely capture the PPG signal, it's called remote PPG, and it is relatively more convenient, and we utilize remote RPPG for the convenience. Researchers have also used audio and textual information for depression analysis, and some of the works combine 2 or 3 of these modalities. Although the physiological modality is not fully explored. And interpretability analysis has also not been explored towards multimodal depression analysis. To fulfill these research gaps, we proposed multi-depth-net, where we fuse the multimodal information from visual, RPPG, audio and textual modalities. And we also propose interpretability analysis to understand the contribution of each of these four. We conduct extensive experiments on 4 datasets whose summary is shown in this table. They have depression labels that are classified into 4 classes as per Beck depression inventory. The 2 of these datasets, that is AVEC 13 and 14, have German videos in 480 by 640 pixel, not of very high quality, but it's decent to capture RPPG from the videos. The other 2 have information in English, however they do not provide the raw videos and hence we cannot capture RPPG. We work with remaining 2 modalities for DAIC and extended DAIC. And finally, we evaluate the performance using 6 extensive matrices, which are mean absolute error, RMSE, accuracy, precision recall and F1 score. This is the architecture of multi-depth-net. It has input, feature classification, and early and late fusion phases. Let's discuss them one by one. In the input phase, we have the raw video, which is used to extract RPPG signal. If the audio information is missing, we utilize MoviePy library to extract the audio from the videos itself. If the text information is missing, we utilize Whisper library to extract the text information from the audio. Then we have feature extraction and pre-processing networks, where we utilize MTCNN, multitask cascaded convolution network, for visual modality that detects and aligns the face, resizes it to 224 into 224, and detects the facial landmarks. For RPPG module, we explored various machine learning based and traditional methods, and depending on accuracy and signal to noise ratio values, TSCAN was chosen for final implementation. For audio feature extraction, we use Librosa library. For textual feature extraction, we use Robota library, which converts the text information into embeddings. It requires the text to be in English. So for AVEC 13 and 14, which have German video, we first convert German to English using Whisper library. For classification networks, visual modality uses dual CNN-RNN network, whereas transformer is used for physiological that is RPPG data, because of its ability to capture long-term dependency, which is a useful feature for time-sensitive physiological data. It also addresses the long-term frame forgetting phenomena, and it has been used recently in other well-known works as well. For audio network, we use ResNet 18, and for text classification, we use multi-layer perceptron. Moving on, we utilize both early and late fusion. For early fusion, we combine the information from all four modalities after normalizing them to a consistent scale. Then the information from all four modalities is combined into a single feature vector, which is passed to the fusion network containing fully connected ReLU dropout layers. The advantage of this method is that it captures the interdependencies between various modalities, and architecturally it is simple. However, computationally it is complex to process the high dimensional feature vector. Also, it is difficult to handle when certain modalities are missing, because we have a final encapsulated single vector. To handle the missing modality, late fusion is more helpful. Let's discuss that in detail. The late fusion is based on multi-vis approach, which utilizes LIME, local interpretable model agnostic explanation, in the background to compute the global scores. The global scores are called influence scores, which tell us the modality-wise contribution. They are aggregated to 1, and the values for each modality are used as modality weights. Then we have local score or significance score, which is at the class level. It is important to note that we are combining the information from 4 modalities. Each of them have intermediate scores for depression classes, which are used as ranks. These rank information is used to compute the BORDA scores. We will discuss that as we move on in this slide. So we compute the weight of each modality as obtained from influence scores. We also use the rank from the intermediate score and compute the BORDA scores. These are aggregated, and when we have certain modalities missing, these are adjusted accordingly. We have coefficient alpha. When certain modality K is missing for a sample J, we set this factor to 0. So it is convenient to handle the missing modality for certain or all the samples while using late fusion. And finally, the class corresponding to highest aggregated score is our final prediction class. For late fusion, apart from BORDA score, we explored average of softmax and training the MLP as well, but BORDA score performed the best, hence it was utilized. Now the question is, why do we have 2 kinds of scores, the global and local? We use the global influence score to get the modality-wise contribution, and local significance scores to get the class-wise contribution. It is important to note that we are not changing the model, but we are adjusting our interpretability analysis to explain the model itself. When there is a mismatch between BORDA score and the modality scores, we adjust the parameters like a check and feedback mechanism and recompute and explain the scores. The results suggest that there are some methods that perform good for certain datasets but not for others. Our method performs decently for all 4 datasets. It also gets us the modality-wise contribution, where visual modality performs better for ABEC datasets, whereas audio modality contributes the most for DAIC dataset. We explore certain baselines and incrementally come up with the architecture of multi-depth. We also explore certain ablation studies to understand the impact of missing modalities, also to finalize the architecture of RPPG and visual network. It is convenient to use remote, and our analysis performs better for all the data sets, and it also gets us the contribution of each modality. Thank you for your attention. In future, we will focus on real-world application, focusing on privacy preservation, and the potential application of our work is in telemedicine, wearable tech, remote health monitoring, etc. Thank you.